Okay, we're going to start with an exercise of a synchronous machine. From the exercise, we can see that we have a AS XS of 1 ohm. We have a B line of 480. So our BM is going to be 480 over square root 3. We have a power factor of 0.8. It's telling us that our mechanical losses are 1.5 kilowatts. Our core losses are 1 kilowatt. Whereas it's telling us here that the magnitude of our EV is 480. Okay. So the first that is asking us is to get the speed of rotation. So we know that our synchronous speed is going to be ns is equals to 120 frequency over the number of poles, and that's 120 times 50, that's what it says here, 50 hertz over our number of poles, that is 6. So we get a speed of 1000 rpm. So that's point A. What is the terminal voltage if this generator is loaded with a rated current at 1 power factor? Okay, so we know that PS is equals to our JAS IS plus EB. So here we have a AS of 1, and it's also los terminals that are IS is 60. So this formula becomes AS equals J1 times 60 amps plus EB, that is going to be 480 over square root 3. And this one is going to have an angle psi. So here we're interested in this angle and in the velocity and the velocity and the voltage Vs. So if we make this into a triangle, we are gonna have that in our imaginary part we have 60 amps. We know that our Bs is always has an angle of 0. So here our Bs. And we know that if we add this vector with this vector, we get Bs. So over here we are gonna have our 480 over square root 3. That's 277 in an angle of sigma. Okay. So we can, from here we can figure out the value of Bs, because we know that Bs, the magnitude, is going to be equals to the square root of 277 square minus 60 square. And this is going to give us a 240.4 Bs. So for the question of what is the terminal voltage in this generator, if the current is loaded at 1 power factor, is this 270.4. Okay, now we're going to see another example. They are asking us to sketch the phasor diagram of this motor and find the values of A, IA, IL, and EA. And here EA is what I always call EV. That is our speed dependent voltage source. So they're giving us a bunch of powers. So we know that the power in is equals to the power in the shaft, that is the power out, plus the mechanical losses, plus the power lost in the core. So we can say that our power in is equals to, they're saying that we have a 15 horsepower, so that is 15 times 7.746 to turn it into watts, plus 1.5 kilowatts in mechanical losses, and that is because of the windage, plus 1 kilowatt in core losses. And this gives us a total loss, a total power in of 13,000.6 kilowatts. Okay, we also know that our power in is equals to square root 3 of the line voltage times the the line current, the phase current, time cos of the angle. So now we can plug the values that we have to find the value of IL. So this is going to be 13,690 watts equals to square root 3 of 208 times 208 times IL. Cos of the angle is the power factor, in this case is 0.8. So we have an IL of 47.49 amps in the line. So if we want the phase current, it's going to be equals to the current in the line over square root 3 over an angle of the inverse cosine of the power factor for this particular case, because these conditions are at this power factor. So we have a I phase. I phase are gonna call IES because it's what I'm used to. So 7.7, 27.4 in an angle of 0.64 radians. Always be careful with the angle. If you are working in radians or in degrees. If you are working in degrees, make sure to put the degree angle. Okay? So RBS is always JXS, our current, plus our speed dependent source. So here they are asking us for, well, we found IA, so, and we found the current in the line, so we are now need to find EA. That, well, I call EV, just for consistency. So we know that from this, we are gonna get that our EV is gonna be our BS minus JXS IS. By plugging what we got, we say we have that 208 minus J 2.5 that is given, and this multiplying what we just found here. just gonna write radian so it is clear. So we have an EV of 255 with an angle of 0 minus 0.21 radians. Okay, so now that we have our our two voltages and our current, we can sketch the phasor. So we can start with BS because we know that it has an angle of 0. So this is gonna be our BS. Uh, Now over here we are gonna have IA that we found here and has this angle of, if we turn it into degrees, is 36.7. This is gonna be our IA. And over here is gonna be our EV. And we know that between these two, when we subtract our JXS IS, we get our BS. Yeah, so this would be our phasor diagram. Now for B, it says that the shaft load is increased to 30 horsepower. Sketch the behavior of the phasor in response to the change. Okay, so this means that the power in the shaft, no, the shaft load, yes, the power here changed to from 15 to 30. So now we can use this angle. So we need to calculate again. We need to figure out how to get the angles for our IA or for our new EV. But now we know at least that our magnitude of EV will not change because we know that this depends on the speed and in the current of the rotor. We know it's a permanent magnet. So, but if we had like a one rotor with a constant current, that would be a permanent magnet too. So, but still, the only thing that changed was the power. So this magnitude is not going to change. Um, Now for what we did in here from this phasor that we drew when we were figuring out the values, we can see that our xs is cos theta is equals to EB sine of psi. So here is what we figured out, that these two were equals. And we can also see that our EB cos of psi, so here we have psi, where here we have psi, and the adjacent will be this one. And so we will have BS and we will have whatever is here. So we know that this is going to be equals to BS plus XS IS sine of theta. So now we have these two equations to work with. So first, let's figure out what is the power in. That's going to be square root 3 of the voltage in line times the current in line times the cosine of the angle. uh, we know that our power in change because before we had this, But now we change this to 30. And when we do the change, we are gonna get that we have a new power of 24,880 watts. So we know our power in, we know our line voltage. What we don't know is the cosine, the theta, and the IL. So we can plug what we know. We know this. We know square root 3 of 280 is our line voltage, and we don't know these two. So we know that this is equals to this power in over square root 3 times the line voltage. Okay, and remember that the current in the phase is equals to the current in the line over square root 3. So when we multiply this times square root 3, eventually we will get rid of this. So we can say that our I phase times our cos theta is the same, but instead of a square root 3, it's gonna be just 3. Okay. Now we know that xs times is cos theta is equals to EB sine psi. That is what we just figured out. So we know this, that is our what we got here, and we know this value. So we can plug it in. So we have 2.5 times this is gonna give us 39.87, and this is equals to EV. We know that the magnitude did not change, a sine and psi. So if we solve for the angle, we are gonna get it's gonna be the inverse sine of 99.675 over 255, and we get a sine of 23 degrees. Okay, now that we have our angle, we can say that EV sine of psi is equals to PS plus AS IS sine of theta. That is what we figured out by here. And since we have these values, we can say that 253 times 0.92 is equals to, we have this voltage plus we have this impedance, and we don't know these two. So now we can solve for IS sine of theta. Now I'm using IS and I phase interchangeably just because we use IS to figure out the formulas, but this is the current in the phase. Okay, so IS. So when we do this, we are gonna get that our IS sine of theta is equals to 10.69 amps. And before we figured out that IS cos theta was 39.87 amps. So now that we have these two, we can figure out the magnitude of IS by squaring these two. So this square plus this one square. And our magnitude is gonna be 41.23 amps. And now that we know the magnitude, we can figure out the angle. That's gonna be minus cos of the opposite is over the magnitude, 41.23, and we get 14.75 degrees. Okay, now we can draw the phasors. They are not my best work. But here we can see that the magnitude of IB did not change. Instead, the same. What changed was the angle. Our IA went from negative to positive. And if we see our power factor, that's going to be cos of 14.75. We get a better power factor. Okay, so just be careful with these exercises, because you will think that you can keep using the angle from the power factor, but that's not the case. Okay, for the next exercise, sketch the initial factor. Okay, so we know that by now we can know that our current in the phase is equals to the power in over 3 times the voltage in the line times the power factor. That's what we did before, mainly. So we can say that our current in the phase is going to be equals to our power in, that is going to be this 15 horsepower and 46 plus 1.5 kilowatts plus 1 kilowatt. All of this over 3 times 200 is just the same of our last example, 35 with an angle of minus cos power factor. Now we know it says that this is lagging, so we know that this angle is going to be negative. So our I phase is going to be 25.8 with an angle of minus 31 degrees. So just gotta be careful when it says lagging or leading. If it says lagging, we have to make the angle of the current negative. And now it is saying that sketch the initial phasor of this motor and find the values of IA. We just found IA, so EV is gonna be, I know they call it EA, but I like to use the formulas that we figured out. So EV minus JASIS. I hope it's not too confusing. So EV is gonna be 200 minus 2.5 times 25 point. Now remember, here we are using the power factor angle because this is the initial condition that they are giving us. So EV is just gonna be 183.3 with an angle of minus 70 degrees. And when we draw this phasor, it's going to look something like this. Okay. So now it's telling us if the flux is increased by 25%, sketch the new phasor diagram. Okay, so if the flux is increased, we know that our EV is going to increase. We know that the flux, the EMF is equals to the number of turns to the derivative of the flux of time. So if the flux increases, the EMF will increase. Also, we can see it as, we know that our formula for EV is equals to omega x if. Oh, wait. Let me see the formula here when we figure it out. The very beginning, steady state, yes. Yes, so this is our formula for EV. Let me put it over here. So if our flux increases, our IF increases, that increases our EV. So what I'm gonna say is that if our flux increases 25%, then our EV increases 25% too. So now we can see that our magnitude in EV increases. That is different from the last exercise where it stayed the same. So the magnitude in EV increases when the current in the rotor changes, but the magnitude stays the same when the load changes. So now we are gonna have here L naught, well not L naught. We know that our magnitude is gonna be 76 degrees. So we know this is our initial magnitude. If we increase it 25%, is gonna be, our magnitude increase is gonna be this times 1.25, and our new magnitude is gonna be 29.125. Okay, now we know that our power, when we neglect our stator resistance, is equals to 3 Vs EV sine of psi over Sx. So now we know our new magnitude of EV, but we don't know our change in our angle. So we can say that an angle is equals to sine to the minus 1 equals to as times the power in over 3 Vs EV. Now, if you look at this equation, since we are not changing the power, but we're changing this magnitude, this relation between our, we know this is constant, our Vs doesn't change. So this relationship right here needs to change to maintain this value constant. And that's what we are seeing here too. So we know that our angle has to change. And this is gonna give us 13.9 degrees. And now to find our our current. We know we have here our formula, and if we solve for current, we are gonna get that is gonna be Vs minus EV over AS. So our current needs to change to account for the change in EV. So our IS is gonna be 208 minus 129, 1 in an angle of 113.9 degrees over J 2.5. So we get our IS of 22.6 in an angle of 13.9 degrees. Make a plot, yes. Now, okay, this was positive when we did the new calculation. So our new power factor is going to be cos of 13.9. It's going to be 0.97. Okay. And now if we draw the diagram, we are going to get something like this. Okay. Now they are asking us to assume that the flux in the motor varies nearly with the fuel current. Make a plot of AA base source IF to the synchronous motor with a 15 horse power load. Okay. Now, if we think about it, our current, when our current in IF, when our current IF increased, yes, when IF increase, our IA has to decrease. So for this, let's do it in MATLAB. So here we see the V curve. So we have our initial parameters. We have our 15 horsepower, and we have an L naught, a random L naught, just to have our equation of EV times omega S times L naught and IF. And here I'm changing IF from 50 to 350 and doing it with a 60 hertz. And here we just have the calculations that we just did to get our IS. And I'm saving our IS into a vector so we can plot it. So when we run this, we can see here we have our, on the x-axis, we have our IF and we have our IA in our x-axis. So if we are in the lagging side, as our current in IF increases, our current in IF increases, our current in IA decreases, until we'll get to the point where we have one of power factor, and then they follow each other. As the current in IF increases, our current in IS increases as well. So this is called the V curve, and is the response is what we get when we plot our IF versus IA. Okay, I hope this one helped here. Now let's go back to our drawings here. Now let's do some induction motors to start seeing the difference of the calculations when we have an induction motor and a synchronous motor. So we have here an induction motor. It's observed at a speed of 3.3502 RPM. Okay. It's not letting me. Okay. Now we can see the whole thing. Okay. So they're asking us for the power. So it's good to remember what is the power flow in an inductor motor. So we know that we're going to start with a bunch of power in. Then the first losses that we are going to get are in the stator and are going to be the copper losses. So this is going to decrease the power. Then after the copper losses, we are going to get the stator core losses. So that's going to decrease more the power. Then we are going to have when we have the stator losses and the core losses subtracted, we know that everything else is transferred to the rotor, so we have the air gap power. So from now we have losses in the rotor, so we are going to have the rotor copper loss. That's going to decrease the power. Then we're going to have, after we have the copper loss in the air power, we know that the rest is going to be our electromechanical power. And then we're going to have the rotor mechanical losses. And whatever is left is the power out or the power in the shaft. Okay, so this is the power flow in an induction motor. And it is telling us here that the R power, I square R power dissipated in the rotor. Okay, so remember we have three lines. So the stator copper loss is gonna be 3 R I squared. Not just one R, it's 3 because it's 3 phases and we have losses in each one. And from this, if we write it in formulas, we know that our power in the air gap is equals to our power in minus our power copper loss. So we have that our power in our air gap is gonna be 15.7 kilowatts. That is given here. And we know that we have a copper loss of 3. R is given 0.2 ohms times I, that is also given 22.6 squared. So we can say that our power in the air gap is going to be 15.4 kilowatts. Okay, now just to remember, our model for our induction motor was something like this. Sorry for the ugliness. Where here we have our copper resistance, we have our inductance in the stator, we have our inductance in the rotor, we have our magnetizing inductance, and here we have our resistance in the rotor over our slip. So this is what we figured out last time. So they are asking us to calculate the dissipated in the rotors. Okay, so we are gonna need the power dissipated here. So first we need to calculate the slip. That's gonna be 120 times the frequency over the number of poles. Here we have 120, frequency of 60 and 2 poles. So we have 360 RPM. So we know that our sleep is going to be equals to our synchronous minus our rotor speed over our synchronous. And we just calculate our synchronous. Our rotor speed is given. So we know that we get a slip of 0.0227. So it's around 2.7%. Okay. And before we figured out the formula for our air gap power, that was 3I squared times R2 over this slip. And what we have over here is the rotor copper loss. If you see, this formula is just like the formula for the stator copper loss. It's just that we are dividing over the slip because we have here this model of this variable resistor. So if we multiply our slip by our air gap power, we get our rotor copper loss. So our rotor, just gonna write it as PCU, is gonna be equals to our slip that we just calculated, 0.0227 times our air gap power that we also calculated over here. And we get a copper loss of 419 watts. Okay, so this is a way of calculating the losses in the rotor. And here we were not giving mechanical losses, I think. Yes, just for the stator. Okay. Now let's go to the next exercise. Also for an induction motor. Make it smaller so we can see it. Okay. So again, here we are giving the values of the resistance and inductance. So again, let's draw our model so we can kind of see what is what. We did an exercise just like this in another video, it was really close to it. To our S. Here we have our S naught. Here we have our 2.94. This is our R1. This is our X1. 0.043. This is our X2, 0.209, and our X0 of 13.25. They call it, it's not called it XM because for mutual. Okay, they are telling us that we have a slip of 2%. So the slip is this. And they are asking us to compute speed. Okay. So again, our speed is ns, 120 times the frequency over the number of volts. We have 60 hertz, but now we have 6 volts. So this gives us 1200 RPM. Now, they're asking us to find torque and power, okay? But to find this, we first need to find the stator current. So when stator current, yes. We need to find a stator current to find our rotor current so we can find our power and torque. Okay, so let's start with a stator current. is. And if we look here in our circuit, here we have our Vm, and we are going to have that is going through here. So to calculate is, we need to get the total equivalent impedance, and we divide by our Vm, our Vm over our total equivalent impedance. So this is what I said that we did really close in another, and we figured that our totally equivalent impedance was these two in series plus these two in parallel. So we have Js naught plus Js2 times Jx2 plus R2 over S over Js naught plus Js2 plus R2 over S. Okay, so if we plug everything, we get 0.294 for R1 plus Jx1 plus J0.53 plus all of these values that we just have over here. Just gonna move it here. Okay, so we calculate our total impedance of 5.7 in the real part plus J 3.6. Okay, so now we can calculate our IS. It's gonna give us 120 in angle of 0, 127 because we know that our line to line is 220, so our Bm is going to be our line to line over square root 3. Okay, now down here we have our equivalent impedance, and this is give us an 18.83 in an angle of minus 32.3 degrees. Okay, and now for IR, we know that we have here a current divider, and we're interested in the current going here through this side. So we know in our current divider we are going to have x naught on top. So our IR is equals to minus IS, minus because it's going the other direction, Jx naught over R2 over X plus Js2 plus Js naught. Okay, and we just plug the values and we get our rotor current of 6.34 in an angle of minus 4.70 degrees. Okay, so if we go back to our power flow, we can see that lead, output, torque, and power. We need our output power. So first, let's get from here for what we found. Let's figure out our power in our air gap now that we have our current in our rotor. And we know that the formula for the power in the air gap is equals to 3 times the magnitude of IR squared times R2 over S. We have all the values, So we can just plug it. Square times 7.2, 7.2 because it's divided by the slip. And this it was 5,753 watts of air gap power. So if we look here to our power flow, we know that our output power is our air gap power minus our losses. Our losses in the copper and our losses in the rotor mechanical losses. So we have the power in the shaft is equals to our power in our air gap minus our copper losses minus our mechanical losses. And we also figured out in the last exercise that our copper losses, our power in copper losses, was equals to our slip times our power in the air gap. So we can say that our power in the shaft is equals to our power in the air gap that we just figured out here minus 2% of this, that is 150 watts, 15 watts, minus our mechanical losses that it's given in our exercise, and that's 403. So we get a power in our shaft or a power out of 52,235 watts. Okay. Now it is asking us for the output torque. Now, output torque is different to output developed torque. Our developed torque was our power, electromechanical power over our omega s. But our output torque is going to be equals to our power in the shaft over our omega s. So to figure out omega s, we know that we have the speed in the rotor, and we just need to multiply it by 2 pi over 60 to get radians per second. So we get 176 times 2 pi over 60, and this gives us 123 radians per second. Okay. So with this, we can say that our torque in the shaft is equals to 5235 watts over 123 radians per second, and this gives us 42.56 newtons per meter. Now they are also asking us to figure out the power factor and the efficiency. Okay, so we know that our power factor is equals to cos of the angle in the stator or stator current. We know that our stator current is 118.83 minus 32.3, and we know that this is minus because it's telling us that it's lagging. So our power factor is equals to cos of minus 32.3, so we get a 0.85 power factor. And to find the efficiency that we call N, it's going to be equals to the power in over our power out, and we know that our power out is our power in the shaft, and we know that our power in is our current in the magnitude of the current times square root 3 of the voltage in the line times cos theta, uh, that is our power factor. So we get an N of 6030 over 52,235 watts and watts. We multiply by 100 to get percentage, and we get that is an 86% efficient. Okay, and now let's do an exercise for an asynchronous motor. Just so we get the hang of it. Okay, let's draw the circuit that we figured out for our synchronous motor. So it is an inductance here. We have our speed-dependent source here, and we have our BS here. Okay, and it's telling us here that we have a 60 hertz. Okay, the frequency for our BS is gonna be our 460 over square root 3 in an angle of 0. So we are gonna have 265.6. Okay, it's telling us that our synchronous reactance is 1.68 ohms. Okay, we have a power factor lagging of 0.95. This field current is operating as, we have a field current IF of 47 amps. Okay, so calculate the voltage EF, well, that's what we call EV, in volts, the magnitude on the field armature to mutual inductance, and the electrical power input into the motor. Okay, let's start for finding what is our IS. So IS is equals to 120 in an angle of cos minus inverse cos of our power angle, 0.95. 120 because it is telling us that our terminal current is 120 at this power angle, a power factor, so we can use it. So 120 in an angle of 18.19 degrees, but we know that is lagging, so we have to make it negative. Okay, so now that we have our BS and our IS, we can calculate our EV. That's going to be equals to our BS minus our JXS IS. So we have EV equals to 265.6 minus J 1.68 times our 120 in an angle of minus 18.19 amps. So for our question A, we get an EV equals to 278 angle of minus 43.4 degrees. These are all in degrees. Okay. For part B, they are asking us to find the magnitude of the field to armature mutual inductance. So if you remember in one of the exercises, we saw that our EV was equals to our omega S times the inductance times our current field. So our inductance is going to be our EV peak, the peak value over omega S. That is F. This is peak because remember our inductance is not a phasor. It's just a value, and we know that our speed is gonna be 2 pi times 60. That's 120 pi. We know that our IF is 47 amps. So because we have this in RMS, we multiply by square root 2 our magnitude of EV. We divide by our 125 and multiply by our field current. This gives us 22.2 millihenries. Okay. Now for C, they're asking us that the electrical power input to the motor in kV and in horsepower. Okay, it's easier to find that in kilowatts first. So we know our Pin is a square root of our power in line times our current in line times the cos theta. So our Pin is gonna be a square root of 460 times 120 in an angle of 0.95. Our power is gonna be 90.8 kilowatts. To change this to horsepower, we just need to divide by 746. So 90.8 over 746. This is kilowatts. This gives us 121.7 in horsepower. Okay. Finally, we are gonna see an exercise in power factor correction, because when we are working with this curve in this region, in the region where they are both increasing, our motor is actually acting as a capacitor, so we can use it to increase the power factor. And we are going to see that when we go from here, when we go from lagging to leading, there will be a difference when we have our synchronous motor. Okay, so let's start by just remembering uh, our formulas for power factor. Again, is cos of theta, and we are gonna use here real power, apparent power. So we know that here we're gonna have our triangle. Here is a real power and a power and a cube. We know that Q is gonna be equals to square root 3 of VI sine theta. We know that our P is gonna be square root 3 pi cos theta. And from this one we can say that our BI is equals to P over cos theta, and I'm using this one because cos theta is our power angle, so we can say that our BI P times I is equals to P times over our power factor. We know that theta is equals to cos inverse cos of our power factor, so we can say that our Q is equals to our power, real power over our power factor times sine theta. Finally, we can say that apparent power is equals to the square root of our P squared plus our Q squared. We also know that S is equals to square root 3 of P times I. So our current is equals to X over the square root 3 times B. And if we have this, we can say that our theta is equals to the inverse tangent of Q over P. So I know this is a lot of formulas, but it's just bad what we are going to use for this exercise. Maybe you already know all of this. Okay. So now we have an infinite bus. An infinite bus is just a hypothetical source that can deliver infinite power. Okay. And it has 480 volts. Now, let's start seeing what will happen for each one. We have our load one that has 100 kilowatts, a power factor lagging of 0.78. This is lagging, and a theta of 141.3 degrees. We found theta by cos inverse of this. We have a load 2 that has a power of 200 kilowatts, a power factor of 0.8, also lagging, and a theta of 143.1. And finally, we have our load 3 that has 150 kilowatts. Yeah, load 3 has 120 kilowatts. Okay, so for this one, our power factor is gonna be, at the beginning, is gonna be lagging. It's gonna be 0.85. So we are gonna start by calculating this. Case 1. Our PF, our load 3 power factor, lagging. Okay, so the total power in the bus is going to be the power in 1 plus the power in 2 plus the power in 3. So the total real power is just going to be 100k plus 200k kilowatts plus 150 kilowatts. So this is going to be equal to 450 kilowatts. Okay, and now we need to figure out our reactive power, and our total is our PQ1 plus PQ2 plus PQ3. And as we figured before with the formulas, we know that PQ1 is our real power 1 over our power factor 1 times sine of the angle theta 1 plus P2 over power factor 2 times sine of the angle theta 2 plus P3 power factor in 3 times the sine of theta 3. Okay, so for this one, well, we have all the values. We have theta, we have the power factor, we have the real power. So it's just plug the values and we are gonna get a total of 323 kilo VAR. So now we can calculate our apparent power. That's our real power squared plus our reactive power squared, and those give us an apparent power of 54 554 kilo ABA. Okay, so we using the formula that we figured for current, we say that we're gonna have this over square root 3 of the line voltage just times the rail voltage, and we get a current of 6.664 amps. And this is with an angle of Q over T, the total reactive over the total real. We get an angle of minus 35.7. Okay. Now let's do the other case. If low case 2, low 3, power factor leading. We know that we can change this by increasing the fuel current. So for this, I just made it in MATLAB, so I don't have to do all the calculations again. So it's the same. We get our bus and our powers. We calculate our total real power, total Q, and with the figure our current angle and magnitude. And we get a magnitude of 565. So I'm just gonna write both cases here. Case 1 is just doing the same, all the calculations, but changes this angle for power 3, this angle to negative. So according to the exercise, the power PLL is equals to 3, the apparent power squared times R. And for our case 2, that gives us a 3 times 565.9 square R. So if we calculate the percentage reduce, it's gonna be this minus this over this times 100. So like this we can see what is the percentage that we reduce in loss, in the loss in the line. So well, from here we just need to, we know that we have 3R in each case, so we can just cancel 3R, and we are just left with the squares. So this is going to give us a 28% reduce by changing the low tree from lagging into leading. And as we saw before, this is possible by changing the current field, so they are both increasing at the same time. Okay, I hope this helps. That is it.